right. I wanted to go through the remaining homework problems in case you had any questions on those. All right. First one I'm going to go through is chapter 14, number 34. So you have your CO gas plus your 2H2 gas yielding CH3OH gas at 500 Kelvin. All right. So the problem gives you the initial moles of 0.1500 moles and the volume of 1.5 liters. So I always convert to molarity. All right, and so I converted my CO to molarity, and I got my 0.1 molar, 4 sig figs, 4 sig figs. I'm going with the 4 sig figs. For the H2, they gave 0.3 moles for the H2, and again, a 1.500 liter flask. All right, and so you've got your 0.2 molar. So your concentrations were converted to molarity. 0 for your methane or CH3OH. All right, and so the reaction has to go to the right. You cannot have a 0. So minus the coefficient of 1x minus the coefficient of 2x plus x. So at equilibrium, we have 0.1 minus x, 0.2 minus 2x, and we have x. In the problem, they say that the concentration of CO at equilibrium, well, they give us the moles, 0.1187 moles, and it's in a 1.500 liter flask. And so our equilibrium concentration of CO is 0.07913. All right, and so we also know that that's equal to 0.1 minus x. So our CO concentration at equilibrium is equal to 0.1 minus x, and that's equal to 0.07913. So we can then solve for x. So when we take our 1 minus x is equal to the 0.07913 molar, we get our x value of 0.02086. The 6 is repeating. All right, and so our concentration of the hydrogen is 0.2 minus 2x, so we take our 0.2 minus 2 times the x value here that we calculated, and we get our equilibrium concentration of hydrogen to be 0.1583 molar. And our concentration of CH3OH is x, and x is 0.02086 repeating, or just put that rounded to 7. All right. So the question asks how many moles of each substance are in the flask at equilibrium. All right, so the CO moles were given in the problem. So that is the 0.1187 moles of CO. All right, we have our molarity of hydrogen, 0.1583 moles per liter. It's in a 1.5 liter flask. That gives us our 0.2374 moles of hydrogen. The methanol, which was 0.02086 repeating moles per liter, times the 1.5 liters, so that the liters cancel. And so your answer to this problem is, in this one, you have your 0.03130 moles of your CH3OH. All right, so those are your answers. It wanted to know the moles of each of those at equilibrium. All right, I always do things in molarity. I was going to do the calculate Kc, and then I read problem number 14.46, which says calculate the Kc in this problem. All right, so Kc, products over reactants, it's our concentration of CH3OH over the concentration of CO and the concentration of hydrogen squared. So we just put in our equilibrium concentration. So your CH3OH you see right there is the 0.02087. So the 6 repeating rounds to 7. All right, and then the equilibrium concentration of CO is the 0.07913. And then our equilibrium concentration of hydrogen was the 0.1583. It is squared. When you push the buttons, everything here has 4 significant figures, and so 3 or 4 significant figures here would be fine. 10.5 or 10.52 is your answer to number 1446. All right, in 42, we have the reaction given, we have a Kc given. All right, so we have this reaction, we're given the Kc value. Then it says, what is the Kc for this reaction? So you have to know, what did they do to the original reaction in order to get this one? Well, for one, you see that the CH4 used to be a product, now it is a reactant. So they reversed the reaction. When you reverse your reaction, you have to take 1 over your K value. That is not where it stopped. They also multiplied through by 1/2. And so you have to then take that to the exponent of 1/2. So when you multiply through by a number, that changes your exponent. When you reverse a reaction, you take 1 over that K value. So this is 1 over the K value, 1 over the 27.8, raised to the 1/2, and your Kc for this reaction is 0.190. So you need to know what to do to your reaction if you reverse it, if you multiply it through by a number, and that is what you do. You reverse it, you invert it. When you multiply it through by a number, the number here being a fraction, 1/2, you raise it to that power. All right, 1452. All right, so 1452. The Kc of this reaction is 0.0952 at 227 degrees Celsius. Always convert all of your temperatures to Kelvin, and that is 500 Kelvin. All right, and so now it says convert your Kc to Kp. You look on your equation sheet, you have your Kp is equal to Kc RT to the delta N. All right, delta N is the number of moles of products, which we have 3 moles of gaseous products, minus the moles of gaseous reactants. We have 1 mole of gaseous reactant. So our delta N, 3 minus 1 is 2. So that's what we're going to put here. All right. So you have your equation. So you put in your Kc, that is given, 0.0952. The R value, you have to know, there's 2 different R values. Kp is in atmospheres. So you have to use the 0.08206 liter atmospheres per mole Kelvin in this equation. And your temperature, again, must be in Kelvin, 500 Kelvin. You also have to do the math right. You have your parentheses. So you have to multiply these 2 numbers, and then you square it. Then you multiply by the 0.0952. You get a Kp equal to 160. All right. So the next problem that we get is CH4Cl solid goes to NH3 gas plus HCl gas. Then it just says give the expression for Kc. So here's where you have to know you do not include solids or liquids, gases and aqueous only. So it's simply the concentration of NH3, concentration of HCl. Part B, same question, give the Kc expression. Again, you have a solid here, do not include it. Your product, CO2, N2 squared over N2O squared. And then the last one, they give a reaction, or not the last one, part C. Here's a solid, it's not included. Here's a liquid, it's not included. Here's a solid, it's not included. The only one that we're going to include in our Kc is the CO2. So you have no products to put in, so just put 1 over reactants, CO2. All right, and then here, aqueous does go in, solids do not go in, and so there's no product, so you put the 1, concentration of Fe plus 3, concentration of OH minus raised to the 3rd. So make sure you know to not include any solids or liquids in your Kc expression. All right, in 58, it just says, is this reaction going to completion or not? All right. The Kc of the first reaction here is 10 to the 113. That is extremely large. You can't include that number in most calculators. It is too large to put in most calculators. So that's an extremely large Kc, which means basically you have all products and you have no reactants. And so this goes to completion. course, you can't have a zero. It's going to be an extremely tiny number, but it is so small, it is essentially zero. It is all products, very, very, very few reactants. So we say something that has a large K value, we say that that reaction goes to completion, right? Again, it can't be zero, but a very, very tiny number of reactants left. All right, now if you have a K value that is 10 to the minus 16, now you have a very small Kc. All right, and so the reaction pretty much stays almost completely as reactants. You're going to have very, very small concentrations of products. So this essentially doesn't go to the right at all. All right, it has to go some very, very small amount. All right, so that's what you get from the values of your K value. It's the concentration of products over reactants. In 1462, we have our reaction. Everything's a gas. We have our Kc set up. And so the Kc is given. It is 3.59. All right, so then they give us conditions and ask, is the reaction going to go to the right? Is it going to go to the left? Or is it at equilibrium? All right, so we need to find out which way the reaction will go. Well, we have to solve for Q. Q has the exact same expression as K, except these are non-equilibrium concentrations. All right, so you put in your CS2 at 1.43, you put in your H2, 1.12 raised to the fourth power. Do not forget to raise that to the fourth power. Divided by your CH4, 1.26, and your H2S, 1.32, raised to the second power. When you push the buttons, you get a Q value of 1.02. So your Kc is equal to 3.59. Your Qc is 1.02. All right, so you see that your Kc is greater than your Qc. So this number is too low. For it to get higher, you have to make more products. It has to go to the right to form more products. All right, so the reaction goes to the right. Again, if you put your Kc first, your Qc second, your greater than, less than symbol will point you in the right direction. It is going to go to the right. The next one is put in the exact same thing. So we give different initial concentrations, and we calculate our Qc. This time, we get 3.57. So when we compare the Kc of 3.59 to the calculated with the new concentrations in here, 3.57, we realize that our last number has some uncertainty in it. And so these are essentially exactly the same. They're essentially the same. Exactly. They are essentially the same, all right, within error, because the last digit has some error in it. All right, so they are essentially the same, which means that you are at equilibrium. When your QC and your KC are the same within the last digit, which has some uncertainty, then you are at equilibrium. Reaction does not go left or right. It is at equilibrium. All right. So again, new concentrations to start with, new Kc calculated. All right. So this one's 0.883. This is too small compared to your Kc. So you need more products. To get more products, the reaction has to go to the right. So the answer is the reaction goes to the right. Again, if you write your Kc first, 3.59, and then your Qc 0.338, you see that your 3.59 is greater than your 0.883. Again, it points that to the right. All right, and then another set of data for your initial concentrations, a new Qc value. This time we get 5.13. And so 5.13 is larger than your Kc. So your Kc 3.59 is less than your 5.13. So this is too big. It has to go to the left to get rid of some of your products. You have too many products, not enough reactants. It has to go to the left. Again, your less than symbol points to the left, also gives you that it goes to the left. I would look at the Qc is going to end up being a Kc. What does it have to do? It has to get smaller. That means we need less products, more reactants goes to the left. All right, 1466, you've got your nitrogen gas plus your oxygen gas goes to NO gas. At 2,127 degrees Celsius, your Kc value is 0.00 All right, so the problem says your equilibrium. So this is not initial. You have to read the words carefully. It says the equilibrium concentration of N2 is 0.023. The equilibrium concentration of O2 is 0.031. The question is, what is the concentration of NO at equilibrium? So you put up your expression, Kc, products, NO, quantity squared, N2 concentration, O2 concentration, and you know three of these four things. You know that the Kc is 0.0025, given to you in the problem. You also know that your concentration of N2 is 0.023. You also know your concentration at equilibrium of oxygen is 0.031. The only thing you don't know is your concentration of NO. So you solve for it. So you multiply both sides by the 0.023, multiply both sides by the 0.031, and then you take the square root, and you get your concentration of NO to be 0.0013. And so that looked like it was going to be a difficult question, but it is not a difficult question. All right, so 1474, we have PCl3 plus Cl2 going to PCl5. What happens to our equilibrium? We're at equilibrium, and now we're going to add Cl2. Well, what happens is now we have too much Cl2. We've added some to our perfect equilibrium. And so it has to go to the right to get rid of some of that Cl2. So anytime you add a reactant, the reaction is going to go to the right as long as that reactant is a gas, all right, or if it is aqueous. If it's a solid or liquid, it doesn't make any difference. All right, so then it says, what happens if you remove Cl? Well, we had the perfect amount of Cl, we were at equilibrium, and now we took some out. Now we don't have enough. So now it has to go to the left to make more. So anytime you remove a reactant that is a gas or aqueous, the equilibrium is going to move to the left to form the right amount. All right, 1476, we have our reaction with CO2H2 going to CH3OH. All right, and so this one says, what do you do with the pressure in order to make this reaction go to the right? All right, so what you have to do is you have to find out how many moles of reactants and how many moles of products, but not just moles. Moles of gaseous products, moles of gaseous reactants. So we see we have 3 moles of gas on the left. We have 1 mole of gas on the right. If we wanted to calculate delta N, it would simply be 1 minus 3, products minus reactants. All right. But this one, we know that if we have a very small volume, it is going to go to the side with the fewer moles of gas. So a small volume would be an increase in pressure. All right, and so what you would do to make this reaction go to the right is you would increase the pressure, which will decrease the volume, and this reaction will go to the side with the fewer moles of gas. And in this case, it would go to the right. All right, same question for the next one. What do we have to do with our pressure and volume to make it go to the right? Here we see we have 3 moles of gas on the reactant side. We have 2 moles of gas on the product side. If you wanted your delta N, products 2 minus reactants 3, it would be negative 1. All right, but this one says, how do we make it go to the right? Well, we know that we have fewer moles of gas on the right, so what we need is a small volume, and we do that by increasing the pressure. So you increase the pressure, which decreases the volume. The reaction will go to the side with the fewer moles of gas. In this case, that is going to the right. All right, and then the last one here, you have 2 moles of gas on the left. You have 1 mole of gas on the right. So why they had A, B, and C be exactly the same, but they did. Each one of those, you had fewer moles of gas on the right. So every one of these, you want to increase the pressure to decrease the volume because we want it to go to the right. And every time, the right side had the fewer moles of gas. And so all of those answers are the same. I thought, so anyway, if you had the same number of moles of gas, then it would not have any effect by changing the pressure. They did not give that as one of those. All right, 1482. We have C2H4 gas plus H2 gas going to C2H6 gas. And they say that the delta H is less than 0. Well, if your delta H is less than 0, that means it's negative. That also means it is exothermic. That also means that heat is a product. And so you can write up here plus heat. All right, now the question is, what do we do with our pressure? What do we do with our temperature? So again, for the fourth time, we have 2 moles of gas on the left and 1 mole of gas on the right. So for the fourth time, we have fewer number of moles of gas on the right side. And so we want to increase the pressure, which would decrease the volume, which would shift the reaction towards the side with the fewer moles of gas, which is our product, which is what we want. All right, and so heat. So we can remove heat by lowering the temperature. If we lower the temperature, we can remove heat. If we remove heat, it's like removing a product. Equilibrium is going to shift to make some more. And so low temperature removes heat, shifts it to the right. So in order to get a maximum yield of our product, we want to have a high pressure to shift it to the right. We also want to have a low temperature to also shift it to the right. That is the last homework problem in chapter 14.